Okay. Alright, so today we're going to be doing the lecture for the column. But before we get started on that, I want to cover a few things. So let's go to today. So, yep, I'll go to modules, then we'll click on today's page. And so your first memo, the grades for that, they will be up either today or tomorrow, most likely tomorrow. So I still need to finish grading the abstracts for each section that I have. So this is taking longer than usual, so I apologize for that. Usually I try to get the grades for each memo in by 1 week. But this time around it's taking a long time because I have 3 sections and I want to give you a lot of feedback on the first memo. So it's taken forever in a day. So I'm sorry about that, but usually I try to get them in a lot faster. Basically what I'll do for the next memos, from here on out, I will still try to give you, I'll give you some feedback still, but what I'll do, kind of for the most part, is I'll give you some limited feedback, but I'll give feedback kind of for the class as a whole as well. So let's go to the submission page for Memo 2. So what I mean is I'll give you some feedback, kind of individual feedback still, but just like I did before you guys submitted Memo 2, I gave kind of like a list here for common mistakes or areas for improvement. And so I'll do this all the time from here on out. And hopefully that'll help, because a lot of the things that I have for comments that's on your PDF submission or the rubric, which I'll show in a second, a lot of those are the same for a lot of the class, and it just, like, I keep typing out the same thing over and over again, and that just takes up a lot of time. So again, I'll give you still some personal feedback from here on out, but for the most part, I'm going to just have comments for the class as a whole. And if you have any questions on your individual grade, you can of course reach out to me and I'll explain the reasoning. All right, but for your lab, so I think I kind of touched on this. I hope I did. I sent out an email about this last week, so I wasn't able to talk about this too much in person for the areas of improvement. I don't think I was able to for this class. But I sent out an email, so anyways, I want to go over this again. So one of the things I noticed for the first memo is, I don't know, maybe half the class or so, you guys didn't have captions on your figures and your table. So you need to make sure that you have a caption on each figure and each table that you have. So I'll show what that looks like. Opening up the chat. Okay, so we're going to go to modules, and then resources, and then the memo template. Alright, so again, for each figure and for each table, you should have a caption that's numbered. So if you didn't have that, I will have left a comment on your memo for the first one. So you see here, I have, looks kind of crap right now. Let me open this up in a different tab. Okay, so here we have a table, and again, same thing for a figure. If you have a table or a figure, you should have a numbered caption. So what I mean by that is like figure 1, figure 2, or table 1, etc. And then you have a caption. Okay, so make sure each figure and table is kind of like that.
Professor?
Yeah.
So for lab 2, it kind of already came. The figure itself came with like its own, not just the label, but it came with kind of a description.
Mm-hmm.
So in that case, would it be all right just to put like a label and a number on it, but like the description's kind of already there on the figure type thing, like
Yeah,
for the chart maybe?
those are a little weird because MATLAB can basically have like the caption there, you know.
Yeah,
So for that, yeah, you could do,
you get away with it.
yeah, you could just do like figure two. Um, I would still do it like that. So you could have like figure two, but the caption is the title of the graph that you made in MATLAB. Does that make
Yeah, that's what
sense?
I did. That's what I did. Yeah, awesome.
Okay.
Thank you.
Yeah. Yeah, those are kind of unique, I guess. All right. And let's see, the next thing is so you need a references section. So most of you had a references section, but if you didn't, I will have made a comment on that as well. So I remember that this memo template, I guess I forgot to myself have a references section in here before, but oh, and I didn't add it in this class. That's great. Let me go into my other section. I'll upload this today. So I updated this memo template to actually have a references section. So let's go to that. Most of you did a good job though. If you had references, you had your own section, and it looked fine. But I just want to cover this too. So you need to have a references section. You could call it references or bibliography. I don't really care. But in addition to this, you need in-text citation. So that would be like a reference to the published values that you had for the elastic modulus and the UTS, all of that kind of stuff. Okay, so here you see the in-text citation has a little 1, so it'd be whatever, if it's your first reference, second, third, whatever, have that in text, and then you have your references section here. I don't really care on the format, there's like, what is it, like MPA, is that it? I'm blanking right now, but there's that, and there's IEEE. So IEEE is like for engineering. Do whatever you want. I don't really care on the actual format here because there's different formats, but it needs to look something like this in your references section here. Alright, let's see, next thing. Using the equation editor when you're typing out equations. So this is actually a bigger thing than I thought it would have been. It's not, you weren't like marked down much at all. I think maybe 1 point. But if you're typing out an equation, you should use the equation editor if you're using Microsoft Word, or I'm sure there's similar features in the online document for Google, right? So basically, if you're typing out an equation, use the equation editor. I don't want to see like a little caret symbol if you have like a superscript. And same thing if you're just typing out any equation, for fractions in general, I don't really care if you type that out in line, meaning you don't actually have like a numerator and denominator. You might just type out meters per second on one line. That's fine. But in general, you should use the equation editor, because when I see like the little caret symbol, it doesn't look professional. So just use the equation editor. I know it's a little bit of a hassle, but use that. Mostly that was an issue of concern with the sample calculations. So again, just use that. Next thing. So if you present a figure or a table in the results section, there should be commentary on it. So for the first memo, and it kind of depends memo to memo, but for the first memo, I would recommend like you would have all of your figures, so the stress strain curve for each figure, and then you could have your table where you would talk about where you would have all of the results for your UTS, elastic modulus, yield strength, and your percent error. And then following the figures in the tables, you would have your interpretations. So remember, you need to have those interpretations in this section as well. So that's right here. So basically, you're explaining to the reader what your data, such as your figures and your tables, what they tell us. So for the first memo, that would be kind of comparing all the graphs that you have. So which material was the strongest, and you would reference that figure and whatever that value was. Which one was the most ductile? So we had two different kind of measurements for that. We had the percent reduction of area, So how much that cross-sectional area was reduced because of necking, and then also the strain at fracture. So you would be kind of mentioning some of these things and whether they were expected or not. So the interpretations, they're not too long. It might be like a paragraph or something. And then in the discussion section, you would expand upon that. So you would kind of go into more depth. So if 1045 steel, if that was the strongest, explain, that, because this is the strongest, you'd want that in an application where there's tensile loading going on. You would want that in an application where strength is important. And then for aluminum, that was the most ductile for this material. So that doesn't mean it's bad or anything. I saw that a few times that people would say that, ductile or aluminum was the worst material or something because it wasn't as strong. That's not the case. It's, each material is good in its own unique application. So aluminum would be good if you need an application where it's where you can have your material kind of undergo some deformation. So that's what you'd want to talk about in the discussion section.
So all that's in the discussion, Professor, regarding interpretations?
Interpretations, those are in the results section, but that's
Oh,
kind of brief. So like a paragraph, and then you expand on that in the discussion.
results. Okay, discussion. Because like I was putting commentary or interpretations before the graphs and before the
Yeah,
tables. Try to do it after. Or,
I prefer after, just so like the reader, they can see your results first, kind of digest that, and then look at the
okay,
interpretations.
and you don't really need like a paragraph for each figure.
No,
Right?
no.
Okay, just like at least a paragraph describing all your figures.
Yeah.
Because I
I
kind of did that and I labeled it graphing explanation for one of them, but
mhm.
I did it before, so just try to put it after in the discussion.
Yeah, I prefer after. I probably didn't mark you down on that because it's
Okay.
kind of up to personal preference, but I think, in my opinion, it's best to see the results first and then see the interpretation.
Okay. Gotcha. Thank you.
Yeah. So it's kind of like, it depends on each memo for if you have a discussion after each figure or after like a group of figures. That depends on each lab. But for the first lab, I think it would have been best if you had the 3 figures, or I guess 6 figures, your tables, and then you would talk about all of them because you're kind of comparing the materials. All right, and then the next thing is presenting the results is often better as a table. So I think most of you did use a table when you were presenting like the UTS values, the elastic modulus, and so on. If you didn't, you weren't marked down on that. It's just typically it looks better, or it's easier to kind of parse through the results if they're in a table, if you can do it. Again, it depends memo to memo. Sometimes a table is more appropriate than others, of course. But for the first lab and I think the second lab too, it would look better in a table. But again, if you didn't do a table, you weren't marked down for that. And then in your discussion, okay, yeah. So in the discussion section, from the results, you want to tie it to real world applications. So if we go down here in the memo section, you'll see here, the first thing that you should do is begin by restating the experiment. That's just a brief restating. So for the first memo, it would be, we did a tensile test to look at the material properties for 1018 steel, 1045 steel, and aluminum 6061 T6. And then you would explain the relevance to engineering, kind of the real world application. So emphasize that this was a tensile test and kind of its importance. And maybe give an example for a scenario where tension is important. So I saw like some people, they had, they would say, it's important to know the material properties, and they would give an example for like a bridge, which it sounds okay, but you want to specify a particular kind of scenario for a bridge when tension is important. So not the actual bridge itself, because that's more of a bending stress, but you could talk about like the tension of cables on a bridge or something. Okay, So you want to make sure that whatever you're talking about for the real world application, that it's actually for the experiment that we did. So for the first lab, that was, of course, a tension test. And for the third one, that was the beam, so that would be bending stress, right? So make sure you do that. And then the last thing here is for my comments, right? So like I've been saying, I try to give a lot of feedback on the first lab. And for that, you can, if you go to your assignment page, once I publish this, which again will be either today or tomorrow, I just got to grade the abstracts. So if you go to your assignment, you should see like in the top right, it's not on this page here, but click on your assignment and you should see like, click on submission details. And then you should get to a screen that looks something like this. And you'll see that I have a rubric, and so that will have comments for each section. So I just wrote, random stuff here just as an example. But I'll have comments on each section. But I also write comments on the PDF itself. So for some people, I write more comments on the PDF versus the rubric. Honestly, it just kind of depends. There's no like real good reasoning behind that, but for some people I have a lot of comments on the PDF, so make sure you look at that too. And it'll be something like this. I'm not gonna say yo bruh on your feedback, but make sure to look at that. Okay, so that's the feedback, and again that'll be up either today or tomorrow. Just gotta grade the abstracts. And let's see what else we got. So that's it for the feedback, general kind of feedback notes that I had for the first lab. So keep all of this in mind, and of course, make sure that you look at this memo template. So if you guys didn't catch it in the beginning, to access the memo template, go to the modules page, and then resources at the very bottom, click on memo template. You can check this out. So this just shows kind of the format and a description of what each section should have. But so this is kind of like a more in-depth, I don't know, description of what each section should have compared to the syllabus. But the syllabus has this too. It's just not quite as detailed. So if you go on the syllabus, it'll look like this for each section. Okay. Right. Okay, so now we'll get started on the lecture. So again, the lecture for today is going to be on the column for the fourth experiment that we're doing. So I'm going to go to VKS right now just to give a little sneak preview, like usual, for what the lab is going to look like. So for the first two tests that we did, or first two experiments, we did a tension test. So we had, some kind of rod. It depends. We would have a rod and we would apply tension to it to pull it apart, right? For the first test, we broke them. Second test, we didn't. We kept it within the elastic range. But either way, the first two tests that we did were a tension test. The third test, we had a beam and we had bending stress going on. So our fourth test will be using all of these different rods here. So these are all aluminum 606 1T6, and they're kind of like hollow rods. And instead of applying tension, we're going to apply compressive forces to this. So applying force on the top and the bottom in compression. And we'll see how these rods of different lengths, how they fail. So the short rods, kind of down here, they're going to fail kind of by crushing. And these really long rods here, they're going to fail from stability failure. So they're going to buckle outwards. And then the rods in the middle, they're going to be a kind of combination of the two. They're going to crush a little bit and also deflect a little bit. It depends on how long the rod is. right? And then in this experiment, so we're going to have the 3 different stations that we have available to us in the lab. And each station is going to have different end supports. So one station will be like this, where it's a fixed pin setup. So the top part, we have a fixed support. Bottom here is a pin support. And another one is going to be fix, and the last one will be pin. All right, so you yourself don't need to do every single station, but basically what we'll do is we're going to get data on all 3 stations, and every single person will need to use the data from all 3 stations this time around. So you're going to have a graph that corresponds to this fixed pin setup, one for the fixed setup, and one for the pin setup. But we'll talk about that more next week. Alright, so there's a pin fix. Here's fix pin. Oh, oops, I went backwards. Okay, here's fix. And then we have pin. And so for this lab, we'll talk about this, of course, more next week. But instead of having the software kind of apply the load itself at specified, I guess like a max load, for all the experiments so far, the software, it kept applying the load by itself up to some maximum load, or it broke it, like the first experiment. But for this experiment, we actually need to apply the load ourselves using this hand controller. So basically we're going to use this thumb wheel to continually apply load in set intervals. This dial gauge, we use this to measure the deflection that we have, so the horizontal deflection. But we actually typically don't use this because for the most part we don't actually do this part for the lab, measuring the deflection, because it's so inconsistent. Really, the data is just kind of shit. So let's take a look at this picture here. Alright, we got the short column, and this dial gauge is measuring this outward deflection that this short column has. But it's really hard to find this kind of plane of deflection for these short columns. So, this short column, it could be deflecting outwards here along this kind of plane, or it could be kind of deflecting towards us, out of the screen, or it could be deflecting out here to the right. It's just very hard to initially find that plane of deflection for some of these columns. So the data in the end is really terrible. Not because you guys suck or anything, it's just really hard. So for a lot of instructors, they actually skip measuring the deflection at all. And the only thing that we're going to look at in the lab is finding the max critical load, so the maximum load that we have before the column fails. So we usually just look at that. And that's probably what we're going to do, and it's still a pretty lengthy lab anyways, just doing that and not measuring the deflection. Alright, and then there's one more picture. Here, you can't even see this really in focus, but here we have a really long rod. And you'll see for these very long columns that they're going to fail like this. So there's a lot of buckling that's going on here. Okay, so that's kind of a little sneak preview for the lab. So we'll be doing that next week. Alright. Let's do the fun lecture now for the theory.
So I take it each group will pretty much complete a lab on each separate station, but then when we go to do the report, we'll pull on all 3 groups' data.
Yeah, so each group, you're only going to do it for one kind of setup. So whether it's fix or pin, whatever, you're just going to do that, and that's already going to take up a lot of time. But you're going to be using your data and then the data from the 2 other groups as well. So right. I'll talk about it more next week, but you just got to kind of do the one setup yourself, and you're going to use the data from every single group.
Okay.
Yeah. All right. So, hopefully everyone does a good job, because At that point, when you're talking about the error analysis, if one group messes something up or something went wrong, you're gonna need to know that just from the data that you have. If you're looking at your graph and it looks all wonky, then yeah, maybe something went wrong, but you're not gonna know as well if it wasn't your group. So it's kind of a little bit of a downside there. Okay, so the column. This, just so everyone knows, it's going to be a little bit longer than the lecture for the beam. So we're looking at, I don't know, maybe an hour. Something like that. Just a little heads up. Okay, so again, this lab, we're going to have those different columns of varying lengths, and we're going to apply a compressive load to each column. And then we're going to see when it fails and how it fails. So short columns, they're going to fail, just again as a little preview. Short columns, they're going to fail by yield stress, so it's a material failure. But our very long columns, those are not going to fail by material failure, but they're going to fail from stability failure. So they become unstable physically, and they buckle outwards, and that's why they fail. Okay, so we're going to start this off with a section kind of talking about stability. Alright, so the first two labs when we did the tensile loading, those were stable, so they were statically stable. Alright, so if we have an object under tension like the first two labs, they are statically stable because our tensile forces, they align along the longitudinal axis of that rod that we had. So because of that force, it was aligned along that axis, it was stable. And because it's stable, we didn't see any kind of deflection or anything like that. So the flexure was very, very minimal. We didn't have to worry about that. All we had were those tensile forces that caused the rod to fail. Alright, so again, the flexure is minimal. So what I mean by that is we don't have any kind of like horizontal deflection that's occurring. Of course, we have like vertical deformation because in the first two labs, we are stretching the material. But the horizontal deflection was very, very minimal because those tensile loads, they were aligned along that longitudinal axis. But for compression, once we apply our compressive loads, though those forces, on the top and the bottom, they can tend to become unaligned. And when they become, or misaligned, I guess I should say, when they become misaligned, that's when we have horizontal deflection that occurs. So those loads, they no longer are aligned along that longitudinal axis. They become misaligned, and then we have that deflection that occurs. Okay, so this can occur, from a few different reasons. The loads themselves, they might not be perfectly aligned along the longitudinal axis of the rod. So if they're not perfectly in line from the very get-go, you're going to have issues. So if the top force is, like maybe a little to the right compared to the bottom force, they're going to be misaligned. Eventually, you're going to have that horizontal deflection. Or the rod itself, or whatever column that you have, it might not be perfectly symmetric. And so if it's not going to be perfectly symmetric, those loads, in relation to that, they're not going to be perfectly aligned, so you're going to have that horizontal deflection that's going to occur. So that's just, nature of reality, of course. We're not going to have these ideal scenarios, so we're going to have to deal with these forces being misaligned. Okay, so let's actually define what a column is. Basically, just it's a long, or it doesn't have to be long, but it's a straight prismatic bar subjected to compressive axial loads. All right, kind of a boring definition. Alright, and so our short columns, again, they are going to fail for material failure, which we'll talk about a little bit more. But the long columns are going to fail from stability failure, so they are going to buckle, so I might say buckling, or I'll say deflection. So I mean the same thing though. They will either buckle, or same thing, there's going to be a lot of horizontal deflection that's occurring. And this buckling or horizontal deflection, it's going to occur when we continue to apply our load. And all of a sudden, as we continue to gradually apply that load, there's going to be a very large increase in that horizontal deflection. So in this way, it's kind of similar to like yielding for the first two labs. For yielding, we continue to apply our load gradually, and then all of a sudden, for little to no increase in the load, there is a very large increase in our strain or our deformation. So same kind of thing for the column. We're continuing to apply this load gradually, and then all of a sudden there's this very large horizontal deformation. So deformation along this kind of different axis. All right, and again, that's going to occur for mostly a long column. Okay, so like I do somewhat often, I'm going to use my ruler here. So if we're applying compressive forces to this ruler, right now it's fine. I'm applying a very small load to this, but as I continue to apply load, all of a sudden, we deflect horizontally. So it's buckling now. But of course, this is just a plastic ruler, so we're within the elastic range here, and it's going to go back to its original position.
Professor?
Yeah.
In the first bullet point, what does that word say that starts with a P? I'm having trouble.
Oh, yeah, sorry. It says prismatic.
Well, that's what I thought. I just haven't heard of that word. I'm sorry.
Yeah, it's that's just the formal definition, but basically just, we're looking at a bar. just a straight bar. Okay. Oh yeah, so one more thing to note for buckling. I've kind of touched on this a little bit, but buckling, when this occurs, it's not material failure, so it's not like from yielding or anything like that. It's stability failure. So if you see that sudden large deformation, it's a stability failure. And again, that's from the loads kind of being mismatched. Okay, so now we're going to talk about equilibrium, which is a little abstract, and if you ask me, it's a little weird, the drawings that we use to kind of explain it, but it is important because we're going to talk about equilibrium, and it'll be relevant to what we're going to define next, which is going to be the critical load, or the critical stress in the system. So we're going to talk about 3 different kind of stages of equilibrium. We're going to have like a stable system, an unstable system, and a system that's in neutral equilibrium. So it's not stable and it's not unstable, but it's in this neutral kind of limbo stage. Alright, so to explain this, we're going to have some drawings here. Alright, so if we're in a stable system and we have this ball like in this in the middle of this semicircle, if I apply a load to this ball, either to the left or to the right, it's going to go, up the slope, either way, and it's going to come back down, just because of how this geometry is drawn. Okay, so again, I can go to the left or to the right, but it's going to go back to its original position. You can kind of think of it, I guess, like we're in the elastic range, right? We can apply some load to this ball, and it's going to come back to the original position once we take that load off. Next one is unstable. So if we're in an unstable system, if I move this ball to the left or to the right, well, it's just going to fall off, right? So there's our ball falling off the side of the slope. And then the last one is going to be when we're in this neutral equilibrium. Alright, and here we just have this flat surface, so in the middle we have the ball. If I move it to the left or to the right, it's not going to fall off the edge, but it's also not going to return back to the original position. So basically there's some kind of deformation, or for us, deflection, in kind of relation to the column that's going on here. So I can move it to the left or to the right. It's not going to return to the original position right now, but it's also not going to like fall off here. So it's neither stable or unstable, but it's in this neutral equilibrium. And that'll be important because, again, once we reach something that's called the critical load for this experiment, we're in this neutral equilibrium. This kind of what I call, this like limbo stage where it's not stable and it's not unstable. Okay, so for the critical load, this is going to be the most important part of this lab. So we're going to reach this critical load where, again, we're in this kind of neutral equilibrium. We're not stable and we're not unstable. But once we go past this load, then we're unstable, and that's when we have failure in the column. Okay, so that'll be what we actually end up graphing later on for this memo. Alright, and I'm going to call this P of CR, so P being the load, CR being critical, so critical load. And in your class, so I asked my class yesterday if, for those of you that are taking solid mechanics right now, if you've gone over columns yet, and I think everyone said no, but that's okay. You know, we're still going to, obviously we're talking about the theory right now. We're just not going to derive, you know, stuff from the very beginning, because that's pointless for a lab, but you'll go over that in your class probably. So for this equation that I'm going to write down now, there is a derivation for it, but again, we're not going to go over that derivation. It would take like a full page. So we're going to skip that part. Alright, so this critical load, to restate, it's this transition point from going from a stable system to an unstable system. So we're in the middle there. We're in this stage of neutral equilibrium. Okay, so if our load is less than the critical load, then we're going to be stable. If the load is greater than the critical load, then we're unstable, so the column has failed at that point. Alright, and then if the load is equal to the critical load, that's implying that we're in this neutral equilibrium state. Okay, but basically, no, for all of this, it seems a bit abstract, but really just the main point here is once we go past this critical load, any amount, once we just go past it, then we're going to be unstable, which is implying that the column for us has failed. So that might be material failure, or it might be stability failure, or a combination of the two. But again, this is going to be important for us because we want to find this critical load, and we're going to use this as one of the metrics in our plots that we're going to have. Okay, so there is an equation for this, which is the Euler buckling load equation. But this is only going to be applicable for what we call long columns. That's in quotes here. So we still need to define what makes a long column versus a short column and an intermediate length column. So we'll get to that in a second. But this equation that we're going to write out here, this Euler buckling load equation, it's for the critical load for long columns. Okay, so this critical load that we have, it's for, again, long columns only. This equation is equal to pi squared multiplied by the stiffness, the elastic modulus, multiplied by the moment of inertia, and then divided by the length squared. Alright, so if we're looking at this, basically what it's telling us is the load that we need to have failure in the system, or it's the load where we're in this, it's the max load right before failure. So anything after this load, there's going to be failure in the system. Okay, so if we look at this, we can make our system more stable to prevent failure if we increase the stiffness. So that's a material choice, right? So if I use a material that's stiffer, I can increase that critical load so it's not going to fail at such a lower load. And then besides that, besides material choice, it's geometry. So we're looking at the moment of inertia. We can change how our column is actually made geometrically. So if we increase the moment of inertia, the critical load, that's going to increase. And if we shorten the column, the critical load is going to increase as well. So this is also, as you can see, right, it's to the power of 2. So the length has a very kind of drastic impact on the critical load. So if we make our column shorter, it's affecting our critical load to the power of 2. So short columns, they are going to have a very high critical load, meaning that we need a very large load until there's failure. But a really long column, the critical load for that is going to be very small. So we're going to fail pretty early on. Okay, so next thing is the critical stress. So we have our critical load here, but just like, in the first two labs, we had load and we converted that to stress. Because usually we want to have that conversion, so we're looking at the kind of the material properties. We're not looking at just the individual specimen that we tested, but we're looking at the properties for that material as a whole. So we're kind of taking out that element of the unique specimen that we're testing. Okay, so this will be called sigma of CR, so we have critical stress. So we're just going to take our load and divide it by the cross-sectional area, and then we get our critical stress. What is the first value on the left-hand side of the numerator? Here, this is pi squared. That one, right? We have pi squared multiplied by E multiplied by I. Yeah, pi squared. Yeah,
So can I see the top of the page, or just a little bit higher? Before critical load. Okay. Let me just screenshot. Thank you.
Okay. You got it?
Yeah.
Okay. Alright, so the critical stress, again, we're going to take our load divided by the cross-sectional area, and then we get our stress. So before, I think I said we're using the critical load in the graph. I guess a little incorrect there. We're going to take the critical load and convert that to critical stress, and we're going to be graphing that. Alright, so I'm just plugging in here. So in black we have the critical load, and then in red is the cross-sectional area. And we're going to rewrite this now into a form that's going to be convenient for us later on. Okay, so we have pi squared multiplied by the elastic modulus, and then divided by L divided by K squared. So L divided by K, we'll define this in a second, but this is called the slenderness ratio. And that's going to be a metric to define if we have a short column, an intermediate column, or a long column.
I'm sorry, Professor. Is that a 4 you said?
It's pi squared and then multiplied by e divided by L divided by k squared.
Oh, thank you.
Yeah. Okay, so for the slenderness ratio, I might just call this SR because slenderness ratio is annoying to say. So I'll call it SR. Okay, so that's the length divided by K. And K is just, that's from our moment of inertia and our cross-sectional area. So that is it's a geometric property, right? Because we have the moment of inertia and the cross-sectional area. So it's a geometric property, and it's called the radius of gyration. Okay, so you might see it written as this, where we have k squared equals I divided by A. Or you're going to see k equals the square root of I divided by A. Alright, so again, that's a geometric property because we have the moment of inertia divided by the cross-sectional area. And we use this radius of gyration in conjunction with another geometric property, the length. And if we have the length divided by k, that's the slenderness ratio, or SR, which again, that's going to be a metric to define if we have a short column, an intermediate column, or a long column. Okay, because, so far that's been really vague. What's a short column? What's a long column? So we needed some way to define that. Okay, so our short columns, like we mentioned earlier, they're going to fail by material failure. The long columns, they fail by stability failure, so when they buckle outwards. And the intermediate columns, they fail from kind of a combination, depending if it's closer to a short column or if it's closer to a long column. So we're going to use the slenderness ratio, which we defined, which is L divided by K. And we're going to use that to determine if it's short, intermediate, or long. Alright, so if we have our length divided by K, which is the moment of inertia divided by the area. If that is less than 49.67, then we have a short column.
Professor, before we had a k squared equal to I over A, right?
Mm-hmm.
So then would k in this case be...
No, it's not squared in this case. It's just L divided by K. So it's K squared by itself, the radius of gyration, but it's kind of built in up here in this equation here where we have pi squared multiplied by E divided by the slenderness ratio squared. So you see K squared is up here.
Oh, okay. So if we were solving for k and we had I and A, would we have to do that or no?
If you were solving for k, then you'd have to, yeah, take the square root.
Okay, thank you.
Okay, so we have short and intermediate. So intermediate is in between 49.67 and 63. And then a long column is just going to be where L divided by k is greater than 63. Okay, so that's how we're going to define if we have a short, intermediate, or long column. So, for the lab, we have a variety of columns from, I think, 1 inch to 12 inches. So we're not just going to look at the length and say whether it's short or long. We actually have to solve for this. So we're going to solve for k, like Kevin was talking about, where we have k equals the square root of I divided by a. So we can calculate that. And then we know the length as well, so we get the length divided by k, solve for that, and that'll tell us if it's short, intermediate, or long. And of course, just like always, we're going to be able to do this in MATLAB. So we'll define the length, we'll define the moment of inertia, define the cross-sectional area, then we can calculate k, and from that we can calculate the slenderness ratio, and then we can have our different kind of regions of our graph that we're going to make later on for short, intermediate, and long columns. Okay, so there we go. So far we're getting somewhere. We have the critical stress that's defined here. So we can find the critical stress currently for a short column, or sorry, just for a long column. That's it. So this right here, remember that this is, this critical stress is derived from our Euler buckling load divided by the area, but this is only for long columns. So we can solve for this critical stress, but currently it's only for the long columns that we have, and we know what a long column is now because of the slenderness ratio. So we still need to talk about short columns and intermediate columns, so how can we find the critical stress for that? That'll be later on. But before we get there, we need to talk about end supports. So we want to find the critical stress not only for a long column, but we want to think about the end supports that we have, whether it's pin-pin, fix-pin, or fix-fix. Okay, because these end supports, they're going to drastically affect when our column fails. Okay, so again, these end conditions or end supports, whatever you want to call it, they're going to have a big effect on when the column, we say buckling, but when the column fails. Alright, so far, our theory, even though I haven't mentioned it, this Euler buckling load, it was derived with the assumption that the end supports were pin-pin. But of course, that's not the case. We talked about how you can have fix-pin or pin-fix, whatever, or you can have fix-fix. So we've covered basically one aspect, but we can have those other two end supports as well. And to kind of deal with that, we're going to introduce a concept of effective length. So this effective length, it's going to be the kind of, if we have a different end support than pin-pin, it's going to be the kind of equivalent length of a pin-pin column. So, I don't know, to me, I got to kind of read through this a few times at least when I was first introduced to this, so it sounds a little weird at first, but just think that the effective length is the equivalent length for a pin-pin column. Okay, so let's write that out and hopefully it makes a little more sense. Alright, so the effective length, it's denoted by L sub E for equivalent or effective length. Okay, so again, this effective length, it's the equivalent length for a column that is not pin-pin. So we can have pin fix or fix fix. So again, the equations that we've had so far, the Euler buckling load equation, and then from that the critical stress here, that was derived with the assumption of having a pin-pin column. But we can have the other ones, and from that we can use this effective length. So instead of having length in our equations, we're going to put L sub E. So we can have equations for that to solve for this effective length if we have a pin fix column or a fix fix column. Okay, so we'll show that now. Okay, so here we have a pin-pin column, which is what we've been assuming so far. That's implying that the effective length is just going to be the length of the column, since that's, again, what we've been assuming so far for what our columns have had for the end supports. Alright, then we can have a fixed pin column or pin fix, doesn't matter. For this, our effective length is going to be equal to 0.7 times the length of the column. So thankfully, you know, it's a simple equation. This equivalent length is going to be 70% of the length of this fixed pin column. Oh, dang it. My screen stopped sharing properly. Give me a second. Okay, there we go. So up top here, this is a fixed support, and then on the bottom we have a pin support. And the effective length for this is, again, 0.7 times the length of this column. So that's giving us the equivalent length of a pin-pin column. Okay, and then the last one is going to be a fix column. And the effective length for that is going to be 0.5 times the length of that column. Alright, so we got two fixed supports here, and the effective length is 0.5 times the length of the column. Alright, so again, if we're looking at, this one, we have a fixed column, and this is saying that the effective length for a pin-pin column, or the equivalent length of a pin-pin column, it would be 0.5 times the length of this fixed column. So we're going to basically substitute else of E into L. So instead of having L in our equation up here for critical load and critical stress, we're going to have else of E. So now we can find the critical stress for a long column for these 3 different end supports. So that's good. Now we can do that, but we still need to talk about short and intermediate columns. Alright, so I'm just going to copy and paste. Get our critical load. Critical load. Alright, so that's all I'm doing. I'm just changing L to L sub E for the effective length. And then same thing for the critical stress. Take that. Alright, and then we're putting L sub E right there. So again, this is currently the critical stress for long columns, but it's for every type of end support that we can have. So pin, pin, pin fix, and fix, fix, because we have this concept of effective length. Oh yeah, and then I guess one more thing, we can also rewrite this now for the slenderness ratio. So instead of L divided by K, we have L sub E divided by K. Okay, and that's going to tell us for whatever end support that we have, we can find if it's a short column, a long column, or intermediate. Okay, there we go. Okay, so now we'll finally talk about the short columns and the intermediate columns. So we're getting there, getting to the end now. So to be a broken record, currently we have the critical stress that we can find for any different end support, so fix, fix, fix pin, or pin, pin, but it's constrained for only long columns so far. So we still need something for short columns and for intermediate columns of any end support. Alright, so for short columns, to be honest, it's a bit of a crude approximation. So this is a theoretical approximation for how these fail. So if we have a short column, so we're going to plug in for L sub E divided by K. If it's a short column, we're just going to say that it's going to fail by yield stress. So for the very specific material that we have for the lab, I didn't get this paper this semester, but I got it a few semesters back. We're given the yield stress from the manufacturer. So we're going to assume that this yield stress is when these short columns are going to fail. This is regardless of the end condition that we have. So this is for pin, pin, pin fix, and fix, fix. Okay, so we have our critical stress is equal to the yield stress, which for these specific columns that we have in the lab are 39,177 psi. So again, you're going to see once you make this graph, it's kind of a crude approximation. If I remember right, I think this approximation is a bit higher. I could be wrong, it might be lower, but I think it's always a bit higher than the actual experimental value that we have for when these short columns fail. And this is, a constant, right? So we're going to have a few columns that are short columns, depending on the end supports that you have. But you're going to see once we graph it, it's just going to be a solid line because we're saying this is a constant value. So it's a crude approximation, and that would be a good source of error. Well, this isn't experimental error. It's really just a fault of limitations for theoretical approximations, right? So this isn't an experimental source of error, but you should still talk about this in your memo, because this is, again, kind of a shitty approximation in reality, because we're saying all short columns are going to fail at 39,177 psi when, that's not going to be the case, because as it increases in the slenderness ratio, it should be failing at a different value for the stress. Okay, so just keep that in mind. And then we have the intermediate columns. So for intermediate columns, there is no theoretical equation that has been derived, but there is empirical equations that are made from the manufacturer. So for us, we are given an equation from the manufacturer for these aluminum columns that we have, and they tell us when these columns are going to fail if they are of intermediate length. Okay, so there we go. So here is our equation for intermediate columns, and this is, taking into account whether it's short, intermediate, or long. That's in contrast to short columns where that was just for every kind, right? That was for short, intermediate, or long. We were saying that they fail at this value of the yield stress. But for intermediate columns, just like our equation for long columns, kind of baked into it, we have different SR values, different slenderness ratio values, because we have L sub V divided by K. So for the intermediate columns, we have this equation from the manufacturer. So the critical stress is B minus D multiplied by the slenderness ratio. So B, that's a constant, that's 38,300. And D, that's a constant as well, that's 202. So we're going to get all these, we're going to have L sub V divided by K, which we will already have to find in MATLAB. And then we'll have B and D, and then we can solve for the critical stress for our intermediate columns. So now we have a way to find the critical stress for short, intermediate, and long columns of every single end support type. So now we're good. So now we can actually make a graph, and what our graph is going to be is the critical stress versus the slenderness ratio. Okay, so here we go. We got our critical stress on the y-axis and the slenderness ratio on the x-axis. Okay, and our graph is going to look something like this. So in black here, this is the theoretical graph that we're going to calculate. So just like, what was it? Experiment 3, we're going to have a theoretical curve, and we're also going to have an experimental curve. So in black here, this is the theoretical curve. And there's going to be 3 different kind of sections of importance. So we're going to have a section for short columns, for intermediate, and then for long.
Yeah, Professor, I was going to ask, we're going to have 3 different LE divided by Ks?
You're going to have a lot, right? Because we have, because you have different, you're going to have 12 values, really.
So there's going to be a lot of LE divided by Ks that are all different, right?
Yeah.
Oh, okay, so we'll have like different variables for each one. Okay, thank you.
Yeah, we'll probably make like, I'm just thinking, we'll make like a vector in MATLAB that stores all of those values. Okay, so in the very beginning here, maybe let me draw this a little differently. Okay, we'll draw it like that. So remember, theoretically, for our short columns, they failed by yield stress. So that's a constant value. Okay, so this beginning portion, this is for the short columns. And again, that critical stress is the yield stress. So we're going to put sigma y right there. Okay, that's the short columns, and then we're going to have the intermediate columns. Okay, and then these are going to be the empirical values that we have. So we have that equation right here. Right, and then we're going to have at the very end that this will be the long columns. And for that, we have that theoretical equation that's the Euler buckling load equation, then converted to critical stress. Okay, so there we go. So this, again, it's the theoretical curve here, but experimentally, kind of like Kevin was saying, we're going to have a lot of values for our critical stress and, of course, the slenderness ratio. So I think we have 12 columns in the lab, so that means that we're going to have 12 points on this graph. And remember, we have 3 different setups in the lab. So one setup will be for fix, one for fix pin, and one for pin. So we're going to have 3 different graphs in the memo. So 3 different graphs for each different kind of end support. And each graph is going to have 12 data points on there experimentally, because we have 12 different columns. And then so you'll see it'll look something like this. It's not going to look that pretty, honestly. Hopefully it looks okay. But it also depends. This is another source of error. I guess I'll just tell you now. Unless it's been upgraded, because I know the lab technician Don, he's been talking about upgrading the end supports to more sturdy material. The end supports in the past few semesters, they've been kind of weak. I don't know what they're made out of, but the fixed support especially, it gets damaged. You know, there's like a little nub, right, for the fixed support, and that's in the past it's been easily damaged where it gets kind of bent. So if it's bent, you're already having like a crooked column, so that's going to affect the readings that you have in the lab. So the experimental curve is most likely not going to look, you know, as pretty as this does here, but it should be similar. Hopefully. We'll see though. Right? I mean, you guys already know now that there's always going to be some experimental error in the lab. Alright, so that's what we're going to be doing. We're going to have this critical stress versus the slenderness ratio. We're going to do it for all 3 different setups that we have for the lab, depending on the end supports. And then we're going to compare these theoretical values to the experimental values, and you'll discuss that in the results and the discussion section. Okay. So on the deliverables, once I upload that next week after the lab, I will actually give you the equation. Oh, this is really laggy now. I'll give you the equation for the moment of inertia and the radius of gyration. So they're pretty simple formulas, but I'll give you them on the handout, so you don't need to look them up. And just as another note, once we go to the lab, the loading that we're going to have, it's going to depend on the length of the column. So depending on the actual physical length, because we can already determine beforehand whether it's a short column or intermediate or long, because we have the equation for that. Just take the length divided by k, the radius of gyration. And if we have a short column, we're going to use intervals of loading of 75 pounds. So you're going to start from, of course, 0, use the thumb wheel, go up to 75 pounds, and you're going to keep going in those intervals until you reach your critical load, where, remember, right after that critical load, the column is going to fail. And basically you'll see that you can't apply any more load. That's implying that, of course, it failed. And then for intermediate columns, we're doing intervals of 50 pounds. And then for the long columns, we're doing intervals of 10 pounds. So really different, right? Because these long columns, they're not as strong, because they're going to fail from stability failure first. Because, you saw from our equation that for this critical load, as we increase the length of the column, this is affecting the critical load to the power of 2. So if we make it longer and longer and longer, that critical load is going to get lower and lower and lower. Alright. So we'll be doing that, and I'll talk about this next week too, but when we use the thumb wheel, it's still really sensitive. So when you're trying to do, maybe the technician can adjust this. I can't remember, but again, the thumb wheel is really sensitive. So if you're trying to just increase it by 10 pounds, you gotta barely adjust the thumb wheel. It's very sensitive again, so you gotta barely move it, and then you can do it that way. Because as is, even if you think you're hardly moving the thumb wheel, it's really easy to apply hundreds of pounds. So if we're doing the long columns, you could easily fracture it or have it fail from stability failure without even meaning to, because it's so sensitive. So I'll tell you that again before we start the lab next week. Okay, and the last thing for today, just some recaps. Your first memo, I'll have that graded either by today or tomorrow, most likely tomorrow. So as with everything in life, don't get your hopes up. So I'll have that by tomorrow. And then your second memo, I'll start working on that right away to grade that. And your third memo, that's due next week, so that's due next Friday. So make sure you look at the data reduction video. Make sure you look at the memo template that we looked at the beginning of class, and the syllabus to make sure that you have everything. Look at my feedback for the first memo once I post that either today or tomorrow, and implement that feedback in your third memo so you guys could do better, just to help you out. It's not like the first memo was bad or anything, but obviously look at the feedback so you can just ensure that you can get the most amount of points as possible. Okay, so that's it for today. That's the lecture, so a little bit longer than usual, but that's it. So if you guys have any questions, you can stick around, but if not, I'll see you next week in person, and have a good weekend, all right?
Thank you, Patrick. Have a good week.
Thank
Thanks,
you.
Professor.
Yep. See ya.
Thank you, Professor.
Mm-hmm.
Thank you, Professor.
Yep. See you guys.
Oh, I also just want to say thanks for like responding on Discord, like even at later hours. I appreciate that.
Yeah, that's fine. Yeah, I'm always up really late, so.
Oh, awesome. Me
Yeah.
too. Okay. All right. Have a good weekend. Thank you.
Thanks. You too. Yeah, what's up,
All
JD?
right. So I wanted to double check. I think I had missed when you were going over short columns, the approximation, or I suppose the critical load for a short column. Why is it a bad approximation, and like the source of error? I think I had missed that
Oh,
part.
okay. Yeah, it's bad just because we're assuming that for all of these short columns, like you might have a few of them, depending on your value of LE divided by K, but we're assuming here that all of them fail at that same value of stress when, in reality, as we increase the length, it's going to fail at a bit of a lower value for the stress.
Okay.
So like if we had like, I don't know, 3 short columns here, we're saying that they all fail at this value, but really it should be like the first one might fail here, second is going to be a little lower, and then the third will be even lower.
Okay, that makes sense. So greater the length, the lower the critical load.
Yeah.
Or the critical stress.
Uh-huh.
And then following that, for the critical stress, or at the top of your page there, that's LEK squared, right? Right at the middle,
Here?
sigma CR equals pi squared E over LEK squared.
Yeah. LE divided by K squared, yeah.
LE divided by K squared. And then the other one on the first part of critical stress was pi squared E over L over K squared. Same thing, but just, okay,
Oh, yeah.
Never mind.
Mm-hmm.
All right, well, perfect. I think that was it. And you said the other possible error was the fixed supports, or the end supports, specifically fixed supports, are historically weak and prone to bending, which can alter our results.
Yeah, uh-huh. Yeah.
Okay.
Hopefully it's not the case, but in the past, like, you could, like, even hardly put on the column straight because it was so bent sometimes.
Oh, let's hope we don't break any equipment.
Yeah, well, it won't be you. It's just it was really weak before, so.
Okay.
Yeah.
All right. Thanks.
Uh-huh. Yep.
Professor, can I see the column again on the notes? Because like one of my pieces of paper fell off my table, so I have to just separate it in the right order. Sorry.
Yeah.
I love it. So okay,
Which
it
part?
goes, where we talked about column and buckle, like in the beginning.
Was it the very beginning?
Like right, okay, so the page I have is the one where you drew the slopes with the balls. Yeah. So can I see right before that?
Yeah.
Okay, yeah, that's right after column. Okay, got it. Perfect. Thank you.
Mm-hmm.
That's it.
Okay.
Oh, and then I actually stepped out for the part that I screenshot. I had to step out real quick. But what was that again? The first thing you gave us that was right after, actually the next page after what I just asked about, like after the balls. What was the next? Okay, yeah. Go up.
Yeah.
Right there, the critical load.
Yeah.
That's really not that important, right? That critical load PCR thing right there. That.
I mean, this section here, I guess theoretically not too important, but it is really important for the lab because we're plotting the critical stress that came from the critical load.
Okay, can I write that in real quick, or should I just go to the video and do it?
Oh no, you can write it. I got time.
Okay, thank you.
Yeah. Yeah, it's important though because that's the very last load before it fails.
So in the lab, that's the very last load before it fails.
Yeah.
And then what was the P critical again? That's calculated by us, right? Based on, let me see.
Yeah.
Oh,
This equation?
yeah. So,
Yeah. Yeah, so that's the theoretical critical load for long columns.
so for the short one, that will just be a number, right?
Yeah, short ones are the yield stress.
So then it might be equal for that one, right? It might be, well, close to, right? Or no, I mean like the last P that we have might end up being equal, right? Or something.
And it's always going to go down, so just like
Oh,
the graph here. Oops. Here. So the short columns, they're always going to be higher for that critical stress because they're short. You know, it's going to take a lot of load. But as we go on, once it gets longer and longer, that
yeah.
critical load, it gets smaller and smaller.
Right. Okay. Okay. So then so this part is just speaking to the fact that like as we're increasing P, eventually like while P is less than that, it should be stable, right? And then
Yeah, yeah.
we're increasing P is just the load, right? Yeah. So then like the more we put on that, and the load is given, what was the unit for that again? It's just pounds, right? Pressure.
Yeah, just pounds.
Sorry, I know that's so basic.
No,
Uh,
it's fine.
I'm
Yeah,
not
it's
trying to
pound
stall
force.
you. I'm not trying to stall you, I promise. Okay, that was the last question. I'm sorry.
You're fine, man.
Sorry.
Anyone else? No? Alright, guys, then I'll see you next week.